The topic of today's video will be Cauchy Riemann equations. And as we discussed in the last video, that differentiability condition for a complex valued function has some consequences, and those consequences are just these Cauchy Riemann equations, right? I will start with the differentiable function, complex differentiable function at some point, and that may take that point z, right? So consider suppose fz be a complex valued function differentiable at the point z, right? Or should I write it as fz is equal to u plus iota v, fz equal to u xy plus iota v xy, because u is the real part and v is the imaginary part of the function, and u and v both are functions of x and y, right? Be differentiable at the point z equal to x plus iota y, right? Then the partial derivatives of u and v with respect to x and y exist and satisfy del u over del x equal to del v over del y and del v over del x equal to minus del u over del y, right? So these are called Cauchy Riemann equations. The partial derivative of u with respect to x is equal to partial derivative of v with respect to y. They are equal. And similarly, the partial derivative of v with respect to x is equal to negative of the partial derivative of u with respect to y, and these relations are called Cauchy Riemann equations, right? And this is just a consequence of a differentiable function. If we assume that f is a function which is differentiable at some point z, then the partial derivatives of u and v, means del u over del x and del u over del y, del v by del x and del v over del y, they exist and they satisfy these equations called Cauchy Riemann equations, right? So we'll try to prove these equations, why they hold, means why they are necessary. If a function is differentiable, that then these conditions are necessary, right? Or you can say that these Cauchy Riemann equations are just the consequence of a differentiable function, complex differentiable function, right? So we have a small proof for it, and okay, since fz equal to u xy plus iota v xy is differentiable at z equal to x plus iota y, then by using the definition of differentiability, then f dash z equal to limit delta z tends to 0 f z plus delta z minus f of z divided by delta z exists uniquely, right? Because it is differentiable, then this will exist, right? Right, exists uniquely. And by writing that it exists uniquely, we mean that this the limit of this function exists along any curve through the point z, right? Means the value is always the same regardless of the curve you choose which passes through this z, right? As we discussed in our last video, right? So putting these values, fz is equal to u of u plus iota v, I will plug this value here, and that will give me, first I will write this now u fz, what is fz is equal to uxy plus iota vxy. I want f of z plus delta z. In order to plug it here, f of z plus delta z, fz is given, right? We need f z plus delta z. F of z plus delta z will be given by u x plus delta x, y plus delta y, plus iota v x plus delta x, y plus delta y. This is your f z plus delta z. Means delta z is nothing but it is actually a delta x plus iota delta y. So you have to give an increment of delta x for x and an increment of delta y for y, right? You can see that x has been incremented by this amount and y has been incremented by this amount, and same here, right? So plugging this value f of z plus delta z and fz here in my derivative formula, since therefore f dash z equal to limit delta z tends to 0, this minus this value minus this value, or you will write it as u of x plus delta x, y plus delta y, and minus u x y plus iota will be common, v x plus delta x, y plus delta y minus v of x y, and this is divided by this delta z over delta x plus iota delta y, right? And now since we know that this the value of this limit exists uniquely, so I will choose two different paths, one along the horizontal line and then vertical line, as we have been doing to evaluate the derivative, right? Choose delta z tending to 0 along a horizontal line, and by horizontal line we mean that the value of y will not change along any horizontal line, that is delta y equal to 0, right? And plugging this delta y equal to 0 here, I will get f dash z equal to limit this will become u x plus delta x, right, comma y minus u x comma y over this will be delta x, right, then iota v x plus delta x y minus v x y and over delta x, right? Fine, and we have x here, so limit delta x tends to 0, right? And you will see that this is the partial derivative of u with respect to x. If you know something about the function of two variables, actually u is a function of two variables. You can see from here, u is a function of two variables x and y, right? So whenever you can say u is a function of two variables x and y, then we can differentiate this function u with respect to x as well as with respect to y, right? And then comes the theory of partial derivative. Means you can partially derivate u with respect to x or with respect to y, and they are denoted by del u over del x and del u over del y, right? And this is indeed the partial derivative of u with respect to x, because you can see that there is an increment for x only, y is fixed, right? And that's why we have divided by the change delta x. So this is actually del u over del x, the partial derivative of u with respect to x only, right? And this is the partial derivative of v with respect to x only, right? So ultimately it will become del u over del x, and this will become del v over del x, right? This is f dash z. And since you know that this limit exists, it indicates that this partial derivative exists. Both these partial derivative will exist because this limit exists, right? This is my equation number 1, right? Now choosing delta z to 0 along a vertical line. Choose delta z to 0 along a vertical line, and if the line is vertical, then there will be no change in the value of x, then delta x equal to 0, and plugging this delta x equal to 0 here I will get f dash z equal to limit delta y tending to 0, and this will become u x comma y plus delta y minus u x comma y over iota delta y, or you can write this iota outside, plus iota, and I think that iota will be cancelled. It will become v x comma y plus delta y minus v x comma y over delta y, right, and this iota can be written here 1 over iota. And similar to this, you can see that this is increment in the y only, means this is the partial derivative of u with respect to y, this is partial derivative of v with respect to y, so we can write it as 1 over iota del u over del y plus del v over del y, right, and you can rationalize this with iota, or you will get, or minus iota del u over del y plus del v over del y. This is the equation number 2, right? Fine. So you know that this limit exists, f dash z exists. It indicates that this value should be equal to this value, because approaching delta z to 0 along two different paths must give the same value, means that these two results should be equal, right, in order to that this limit exists. From first and second, we can compare these two. This is a complex number, again this is a complex number, right? You can compare these two. The real part should be equated to the real part, right? From first and second, del u over del x should be equal to the real part of this, and that is del v over del y, and comparing imaginary part, this del v by del x, del v over del x is equal to negative of del u over del y, and these are called Cauchy Riemann equations, right? CR equations, CR equations, right? And you will see that these are the same Cauchy Riemann equations, right? So by this small proof, you should remember one thing, that conclusion, right? Conclusion that if f is, I'm not writing fz, simply writing f is differentiable at z, right, at point z, this implies that CR equations hold at z, right? That is the point. You can write it as z equal to z naught, right? So if a function is differentiable at some point, then definitely CR equations will hold at that point, right? And since this is an implication by implication I mean that whenever there is a statement or combination of two statements, one statement is this statement, second is this statement, and here we have this implication, implies, this is called conditional statement, if then statement. So the contrapositive is always true. Contrapositive is written by writing this first with the negation, not word, and then this thing, right, with not. So it's contrapositive. Remember, it's contrapositive, and that will be written in the reverse way, but putting a not here and here. So I should write it, if CR equations do not hold at z, if CR equations do not hold at point z, it will imply that f is not differentiable at that point z, right? So it can be used as a test to disqualify the function as a differentiable function, right? Because if the function is differentiable, then necessarily the CR equations will hold, right? But it is not the case that CR equation will hold and the function is every time differentiable. The converse is not true. It is a conditional statement. It should be remembered in this direction only, right? Or you can remember this also, right? Because for every statement, its contrapositive is true, its converse is not true. So do not get trapped in the converse part of it, right? Okay. Then, but we need some equation or some concrete theorem to check the analyticity of a function, not differentiability, because as I discussed in our last video, that analyticity of a function is a different task to check, because you need that the function is differentiable at that point z equal to z naught, as well as in the neighborhood points of it, right? And that's a big deal for us, right? So we need something that helps us to check the analyticity of a complex valued function, right? And this will certainly help us, these Cauchy Riemann equations, but together with some extra condition, and together with this CR equations, we have one condition, and that condition is the continuity of these partial derivatives. These 4 partial derivatives, 1, 2, 3, and 4. These 4 partial derivatives should be continuous, and these u and v should be continuous. So that condition clubbed with these CR equations will give a perfect condition to check the analyticity of a function, right? So I'm writing those conditions, I mean criteria for analyticity, right? Criteria for analyticity, right? And what is it, criteria? You can say that necessary and sufficient condition for a function to be analytic, right? So okay, a function fz is analytic if and only if, first condition, del u over del x equal to del v over del y, or in short I can write it as del u over del x, right, is equal to del v over del y, and del u over del y is equal to minus of del v over del x. These are just Cauchy Riemann equations, right? And second condition is the continuity criteria of u, v, ux, uy, vx, and vy are continuous, right? Fine. In that case, you will say that they are analytic, right? Okay. And moreover, if Cauchy Riemann equations are satisfied in at some point, right, and these partial derivatives and u and v are continuous at that point only, then we can say that the function will be differentiable at that point, because remember that differentiability is a point criteria, means we check it by point, while the analyticity is a neighborhood property, right? So in order to function to be analytic, these Cauchy Riemann equations must hold on a domain D, right? Or should I add it here, on domain D, right? On domain D, or should I write it here, function analytic on domain D here? That will be more general. On domain D, now it is complete, right? Domain D if these two conditions hold on that domain. And what do I mean by domain? Domain is an open set, right? Like an open disk is a domain, right? However, the definition of domain is that an open set is called domain if any 2 points of it can be connected by a sequence of polygonal lines, right? I can draw a small domain here. You can see that this is a domain. If I draw this picture, and I'm drawing a dotted picture, right? Because the domain is always open. It cannot have boundary, right? And okay, and the inner part, this part, the inner picture, I can shade it. Okay, the inner portion is the domain, and since I have drawn the dotted points here, it means that it is boundaryless, right? And you can see that if I take this point, let me take these 2 points, and I can join them with the help of a sequence of polygonal lines, with the sequence of lines, and the first line is this line, first line, then second line, and then third line, right? You can join any 2 points in this domain by the sequence of lines, right? Then we call it domain, right? And this is a domain, and an example that is not a domain is that you consider a complex plane, the whole xy plane, and you delete the y-axis, right? Consider the xy plane and delete the y-axis completely, right? And the resulting picture will not be a domain, because you cannot connect the 2 points with the help of these polygonal lines. If you take one point on the left hand side of y-axis, y-axis has been deleted, however, and the right hand side of y-axis, you cannot join those 2 points with the help of sequence of lines, right? So there is an example of which is not a domain. Okay. Now I will move to the numerical of it, right? So I will take the simplest example of an analytic function. Example number 1. Discuss the analyticity of fz equal to e to the power z, right? Solution. And since we have this time we have Cauchy Riemann equations, so we will not be using that limit formula of f dash z, right? Because that needs different paths to be selected, right? I will be going to use Cauchy Riemann equations. So breaking my function in terms of real and imaginary parts, I should write it as e to the power x plus iota y, and then I can write it as e to the power x and then e to the power iota y multiplied by e to the power iota y, and e to the power iota y is actually cos x cos y plus iota sine y, right? And this will give me this implies that u equal to e to the power x cos y and v equal to e to the power x sine y. You can see that u and v are both functions of x and y, right? Okay, now I will check CR equations, and those are the partial derivatives. If you find clearly, if you find del u over del x differentiated with respect to x, you will get e to the power x cos y, and if you find del v over del y, differentiate this with respect to y, that will give you e to the power x cos y, right? And eventually del u over del x and del v over del y are same, you can check that, right? And del u over del y differentiating in respect to y will be minus e to the power x sine y, and this is indeed the same of del v by del x. You can see that, right? Means Cauchy Riemann equations are satisfied, means this point has been satisfied, right? Ux is equal to vy and uy equal to minus vx. But what about this point? U, v, and then its partial derivatives. You can see from here, this is my u, this is my u, right? This is my v, and these are partial derivatives. You can see that every u and v, or these partial derivatives, are continuous. Exponential function is continuous, cos is continuous, and the same thing here, right? Means all these partial derivatives and these u and v are continuous, right? So we can say that the function is analytic, right, based on this criteria, right? CR equations satisfied. CR equations hold, and this is the first part, right? Also, you can see that uv, ux, uy, vx, and vy are continuous, and they are continuous throughout the domain. You can take any x and any y, right? Are continuous on whole C, complex plane, right? Therefore, fz equal to e to the power z is analytic on whole complex plane C. And such functions are called entire functions, which are analytic on the whole complex plane, right? Analytic function. Other examples of analytic functions are sin z, cos z, any polynomial, any constant function, right? Okay. Example number 2. Right. Discuss the analyticity of fz equal to mod z square, right? Solution. Fz equal to mod z is actually under root of x square plus y square, and under root here we have a square, so ultimately it will be x square plus y square, right? And that should be equal to u plus iota v, and comparing you will get implies u equal to x square plus y square and v equal to 0. You can see that the imaginary part is totally missing, right? And if you remember that we have already proved that this function is differentiable only at origin in our last video, right? However, we did that with the help of that f dash z formula. This time I will be going to use Cauchy Riemann equations, finding the partial derivatives del u over del x. You can see that it will be 2x, del u over del y, it will be 2y, del v over del x, it will be 0, and del v over del y, it will be 0, right? Okay. And you can see that del u over del x is not equal to del v over del y. You can see that this is 2x and this is 0, right? And again that del u over del y is not equal to minus of del v by del x, right? You need that ux is equal to vy, but it is not the case. Clearly ux equal to vy and uy equal to minus vx hold means these Cauchy Riemann equations will hold for one condition, if and only if x equal to y equal to 0, right? If you put x equal to 0 and y equal to 0, then automatically these derivatives will be equal. And obviously these u is a continuous function, you can see that, right? And v is equal to 0 is also continuous function, and partial derivatives are also continuous, right? And Cauchy Riemann equations are satisfying only at one point. X equal to 0, y equal to 0 means that is z equal to 0. It means that condition number 1, this condition is satisfied at z equal to 0. Condition number 2 is satisfied for all points, right? But taking their intersection of condition number 1 and condition number 2, condition number first is satisfied for only one point. Condition second is true for all points, right? So the intersection will be that this criteria of analyticity holds just for a single point, and that point is z equal to 0, right? But if something happens, something like analytic behavior of a function happens or true for only one point, then you cannot say that the function is analytic. You will have to say that the function is differentiable at z equal to 0, because differentiability is a point property, while analyticity is a neighborhood property. And you can see that the CR equations are holding at only one point, z equal to 0 only. So the function will be differentiable at z equal to 0, not analytic, nowhere analytic, right? Therefore as z equal to mod z square is differentiable at z equal to 0 and nowhere analytic, right? I think third example. Example number 3, and that is discuss the analyticity of fz equal to x plus 2 iota y. And we have done this example, right? Solution. Here u is the real part, and that is x, and v is the imaginary part, that is 2y, right? And then checking the partial derivatives, then del u over del x is equal to 1, del u over del y equal to 0, del v over del x equal to 0, and del v over del y equal to 2, right? And you can see that clearly ux, that is equal to 1, is not equal to vy in any case. You cannot make 1 equal to 2 by putting x or y something, and but these are equal. Uy is equal to minus vx, they both are 0, right? Uy equal to minus vx, this is fine, but this is restricting us to say that the function is analytic somewhere or differentiable at one point, because they cannot be equal, right? So you will say that fz is not differentiable even, right, at any point. And since it is not differentiable at any point, it cannot be analytic at any point, right? However, the continuity criteria is satisfied here. You can see that u is a continuous function. This is also continuous, and these partial derivatives are also continuous. But due to this CR equations, we cannot say that it is differentiable. It is not differentiable at any point, right? So, in this video, you just remember one thing, that the condition of analyticity of a function is just the combination of those two conditions. The first condition is the Cauchy Riemann equations, and the second is the continuity of partial derivatives of u and v, and u and v also, right? If they both are satisfied on a domain, then we say that they are analytic on that domain. And if they both are satisfied at one point, or one of them is satisfied at one point but the other is satisfying on the whole plane, then their intersection will be taken, right, as we did in our example fz equal to mod z square, right? And these CR equations were holding at just one point, but these derivatives were continuous on whole plane, so the intersection will be this point only. So the final conclusion will be drawn based on one point only, right? So this is it for this video. Thanks.